Good morning, all. Is it audible? Is it audible? Morning, all. Is it audible? Is it audible?
Yes,
Is it?
yes.
Okay, okay, okay. And the screen is visible, right?
Yes, sir. Screen is visible.
Okay, okay. So very fine morning to all of you. We'll start this today's session. So basically today's session, the title is Molecular Representations and NLP for Material Science, right? So I think we'll have a recap of yesterday's session just for a couple of minutes or so. So I think yesterday you have installed this something called as RT kit, and you might have seen about the different types of uh, this thing, import libraries or different types of RDKit libraries. So RDKit is a very vast library, one of the very biggest library in Python. So you can explore more on RDKit. Even biology people can work on this, biochemical people, biomedical people, chemistry people, all these people, not only for the molecular representations. RDKit has got wide number of features and attributes that corresponds to the chem informatics, or otherwise known as polymer informatics or materials informatics, right? So the chem informatics is basically the informatics of chemistry. So basically the chemistry compounds, like the basic of that we have incorporated here as a part of our polymer structure property relations. Okay. So now we can see about these different types of 2D. I think many of them might have given yesterday homework to complete, to try out this thing, like the different types of 3D structures or 2D structures. Those who haven't completed, we can do it as a convenient time. So we have got enough and more examples just to get accustomed with the different types of, say, the structure property relations, I mean the molecular representations. Now the last portion of this I have not covered yesterday. So basically the selfie, smiles to selfies conversion. So basically the selfie is another type of representations, or otherwise known as the this type of representations where they are using the aromatic compounds like benzene, toluene, all these aromatic compounds, especially not only for the chemistry, even for the biochemical or the bioprotein ligands, amino acid ligands. So different types of structures which is having the this type of aromatic structures, the smiles won't be that efficient. So we are using something called as string representations of molecules known as self-referencing embedding structures. So here we have a something called as pip installed selfies. Instead of smiles, you have selfies, import selfies, and we are giving this as a in this aromatic compounds in this form, and you'll be getting an encoding and decoding, right? These are known as the encoded smiles and decoded smiles, where you can see about this, right? So this is the aspect of the smiles and selfies. I think the slides are moving, no, Manat? Manat,
Yes,
slide?
yes,
Yeah,
yes. The
yeah,
slides are
yeah.
moving.
Fine, fine. Now we can see about the different types of selfies to smiles. This is another type of coding where we have seen some conversion, like smiles to selfies and selfies to conversion. Smiles. So those who are into this, those who are using this biopolymers or related to biological materials, biomaterials, or chemistry, the important aspect is conversion of the molecular representation different forms. So this is actually concurrent or adjacent to the molecular representations, which we have already learned or we have seen yesterday. So this is an auxiliary part, which I think during the familiarizations, we can learn it also. So here we are just doing the encoding and decoding and finding input molecule and output molecule and getting this. So this is the thing which we've been teaching for our BTech students, where they are getting exposure with the different types of molecular string representations, or otherwise known as NLP techniques for material science, right? Now we can see from Taylor Sparks. So Taylor Sparks, yesterday I've given a brief introduction about him. He's one of the pioneer in materials informatics. He's a professor at one of University of Utah, at US, where he has substantially differentiated the traditional machine learning approach from the materials informatics. Like here, the traditional machine learning approach, basically, it has got the data downsampling is common. So here, downsampling is something related to the large number of related to computational tractability. So it is basically based upon the number of data sets, data points available. So here he has given a specific or distinguishable area of materials informatics compared to the machine learning. So the Taylor Sparks has given n number of materials in his own YouTube. You can just search in YouTube. He has got a number of YouTube videos connected to this. So if you want to go more into it, this is the best option, and this is the one of the most important resource. Yeah, so I just wanted to ensure that this slide is important, very important. Why? Because you can see to it like what are the different types of. He has its own channel where you can see the n number of videos connected to this. So the data box not only starts from the very humble beginning with something called as feature vector, right? Feature vector means you have a chemical compound. So how you are converting that into vector, right? How we are doing some tokenization. So all these things are related to the that have been developed by data box, right? So now we can see about the smiles to molecular descriptors, where we can see about the different types of descriptors, otherwise known as each smile can be converted to the descriptor forms, and we can see the descriptors are nothing but some sort of tokens available for this. Okay, so here is another type of strings known as inchi, apart from the smiles. I mean selfies. So smiles to selfies and smiles to inchi conversion also you can see. So these are all the extraordinary point which we see. So descriptors coming out of the chemical descriptors, we have the different types of chemical properties. Descriptors are otherwise known as features, right? You have molecular weight, log P, TPSA, HPD, HP, rotatable bonds. So similarly, there are n number of features connected to the chemical bond. So very few have been designated here. So descriptors are basically for each chemical structures, the features of that, or otherwise known as the representations or the attributes or the uh, particular features of there are converted into our descriptors. So descriptors have been generated from the smile states, and you can get the properties of that particular chemical structure based on the descriptors. So I think we can do this alone, right, for today's, because this I have completed. So the previous slides, I think you can learn it together. That is not a problem. So I think you can open the Google Colab. It's like we'll have a hands-on side by side itself. So otherwise you'll be there should be some beneficial right out of the start. So I think we can have this hands-on session right now itself. So you can just note down all these. I think people who are familiarized with Google Colab yesterday, in that same notebook itself, you can just draw this, right? And type this from our Articate import chem. The chem is basically the library, I mean, the particular library from Articate. I'll give you 5 to 10 minutes time. You can just note down this coding statements. I'll post this in the chat box also. You can copy paste also. It will be more easy for you because you have a constant, right? So those who are there active in the online, yeah, yesterday I think very interaction we have with the people. Dr. Anil sir was there, Dr. Raghunath sir was there. So apart from that, I want more interactions today. So please note to that, like we can. I'm just putting in the chat box. You can open the Google Colab. Take 5 to 10 minutes time, and you can just do this. Yeah, this is the first one. And this is the first slide, and continues to that and take me the second one. You can make it fast, as fast you can move. You can move with the more contents. Um, this is the third one. So let us see how it comes. So you can see some outputs coming. So see, spoon feeding you by directly typing. You just need to copy paste it. So people who are in intact, so whether in the skill you can do it, or you can even type. That is the best skill, so you get more exposure to the coding. This is step by step. I'm giving you each slides. I'm converting that into this, and can do that. So AI techniques for material science, or any AI thing, it is basically the coding. You have to code it and practice. Otherwise, it is unable to learn what is this. Right? So it is not like theory, getting a lecture or getting an idea from this. Theory, there is no theory in this, but basically what we are doing is the different types of AI techniques are available. It is at your fingertips. It is there in your Python library itself for any computational packages. So directly you can learn, but how to learn, that is what we are discussing today, and how you can do it, like by directly practicing it out, right? So I think so we can, I think people who are there in line, like have you opened the Google Colab and have you copy pasted this? What is the result coming? Is there any error? You can use the same notebook which you have done opened yesterday, right? I think the practice examples you might have done, even if you have not done whatever you have opened yesterday during the session, that same notebook you can continue because RTKit is already installed in it, right? So this is the idea for this. So just give me exactly 5 minutes. Now it is 10:10. By 10:15, please get back to me. Any, any errors, or if you're not getting, if you're getting, whatever it is, please open your mic and you know, we can discuss with it.
Hello, Dr. Neelesh. Good morning.
Good morning, good morning, good morning, sir. Good morning, sir.
Actually, in the second line, I am getting the syntax error.
Okay.
It is, I think,
Second line.
second line, I think, equal to
Uh,
within quotes CCO, then hashtag ethanol. That is
okay,
showing
okay. You like CCO, have you put in columns, double columns?
double quotes, na? It is under
Double
double
quotes.
quotes.
Uh,
Ah,
that is where syntax error.
okay, I
Like
have to
that.
remove the double quotes.
Yeah.
Okay.
No, you have to put the double quotes.
No, double quotes are already there, but it is showing that.
Sorry. You have to remove the double quotes.
Okay.
Others, please respond. Gita ma'am is there, or anybody. I know only a few people who have responded yesterday. Raghuram sir is there. Raghuram sir is there. Anybody? Like, just need to have
Now,
an
still
interaction. Yeah. Still, it is coming the syntax error, sir.
invalid syntax.
Invalid syntax was fine. So what is happening is yesterday's that code no from import RDKit and import libraries. That again you have to re-import. Maybe today's, I mean yesterday's notebook you have done no. That this thing.
Yes, yes.
I'll just go on. That from different types of libraries are there from RDKit,
Okay,
this
okay, that I don't
import
know.
came, all
Yeah.
these different types of library. Again you have to reinstall it. Others,
That I
please
don't
respond.
know.
Only 5 minutes. This is an interaction apart from the hands-on because I think the time is up, so that I think we can go to the next session. Otherwise, you can practice on your own. Now, I think we can see about the different aspects of polymer and materials informatics, how the mathematics of AI is implemented in the polymer science and material science, right? So I think the screen is visible. So this was the review paper which has been done in 2022. So I'm just starting from the very humble beginning, where is because you should know what is the how the mathematics for AI is being implemented for this. So this paper solely focus on the mathematics part and how this NLP techniques can be imported or incubated in the polymer science. So basically, in this polymer, as we have told, there is something called as structure property relation. Structure property relation is very, very important. That means each structure, like aliphatic or arithmetic or whatever structure which is happening at the backbone of the polymer structure. In the metallic structures, we have, see, for example, different types of aluminum alloys are there, different types of alloys of different carbon is there, different types of iron, aluminum are there, aluminum is there, steel is there. Okay, so for all these, we have something called as phase diagrams, which we have already known. Based upon the martensite, austenite, different temperature, different pressure conditions, the phases changes. But whereas in the case of polymers, there is something called as structure property relations processing. That means based upon the processing, the property of the polymer changes. Why the property of the polymer changes? Because it is directly correlated with the structure of the property, structure of the polymer, which is directly related to the relationship of the polymers, right? For example, the structure of the polymer, you have the different types of chains, like side chains or, different types of bonds between the polymer structure. So we have the covalent bond, different types of angle rotational bonds, okay? So different types of bonds and different types of uh, side chains, which is applicable for the polymer. For example, there is something called as Teflon, like tetrafluoroethylene, CF2, CF2, which we use in our non-stick panels in our kitchen. What is happening? CF bonds is there. So CF bonds is basically, it has got high thermal stability. So that thermal stability is able to withstand the maximum temperature, even if it is heated to 100 degree or even 200 degrees Celsius. That is why it is used for the non-stick panel. So same way, there are different types of material. Polyethylene is used as a plastic covers, like plastic packaging materials. Why? Because it protects the germs, or it protects the microorganisms to enter through permeate or through permeable into the material. So that is based, all these are based upon something called as the structure property relations. Okay. So here, this paper basically envisages about the materials database repositories, benchmarking repositories, data sciences, etc., which contribute towards the emerging field of materials informatics. So how the tools, AI tools and databases of the polymer informatics is explored in this article. So we'll see step by step how it can be. So introduction, basically, we have seen around this 96 engineering, so that I'm just skipping. So I'll just share this material so they can have a read through of this. So here we can see again, I'm talking about only one thing, that is data-driven approaches. Okay. Also allow inverse defined with a desired property is defined and is used to determine the structures corresponding to that property. So this is a very important statement. That means a data-driven approach is used to allow the inverse design. Inverse design means there are two types of design for a polymer. One is you are developing a polymer for a particular property, and other one, the end property is defined and you are doing an inverse design. Okay. So all these attributes to under one roof, that is accelerated design and discovery of materials, right? So for that, how we are using the data-driven approach? This is what we are seeing only. This is basically, the AI is nothing but a data-driven modeling. How you are finding out a new material modeling or predictive modeling or inverse design or accelerated design and discovery of materials, right? So here we can see about how we can see about collective as experience, intuition, or even as a common sense. For example, how you are intuiting, like how you are finding out the solution to a problem, like how you are finding out the predicting a new material from the existing material. So here we can see about the different types of the elements of fingerprinting and data sets. So here the material one, property one, material two, property two, material n, property. Suppose you have the properties P1, P2, etc., Pn. How to do an inverse design. So this is also contributing. So you have the properties, say for example, temperature conditions has to be withstand at above 100 degrees Celsius, or pressure conditions has to be withstand below 200 gigapascal or something like that. So for that particular property, how the different types of materials can be designed. So this is then application for property value and how it can be designated for an inverse design. So here something called as fingerprinting comes to action. Fingerprinting is basically, fingerprints are basically how the general fingerprint. What is that? We are taking a print of the finger, right? Some sort of image taking out of the front. That is known as a fingerprint. Okay, whether we do in using an ink or something like the general print is just like so. The same way, the AI tool is generating the fingerprint. That means a design or an image or a structure representation of a particular material, something called as fingerprints. So these fingerprints attributes directly to the property. So say P1 or P2, etc., Pn. So here the fingerprint is basically conversion of the material, the normal attributes like thermal property, physical property, chemical property, mechanical property, etc., in a machine readable form, F11, F12, etc., in the form of a vector, right? In the form of a vector. So here the maths come into picture. Basically, if you want to move more into it, You can just note it down. Linear algebra, support vector machine, support uh, singular value decomposition, alternating direction method of multipliers, optimization techniques, probability, Markov chain model. All these are the very fundas where you have to get thorough for understanding what is happening behind the machine learning model. Okay. Applying a machine learning model is just like LKG problem. That means directly you can take the ML model directly from the Python or directly apply it, you can get some result. Like how you're applying and design of experiments or how you're doing an FEM model. FEM model you're not doing directly, the system is doing. Same way it is like a package, you're getting a machine learning model, you're doing some comparison. So, apart from that, what is happening behind the ML model? That is how this linear algebra is connected, how it is converted into the vector form. Okay, what do you mean by a singular value decomposition? What do you mean by so that is actually the fundamental of mathematics of intelligent systems or computational mathematics, which we learn or which we give for our engineering graduates from starting from the first year till fifth semester. So we have M1, M2, etc. till M5, where we provide this fundamental understanding of linear algebra, optimization theory, statistics, probability theory, right? So this is an idea for us. Now the second part comes into picture, otherwise known as the learning problem. What is a problem formulation? So generally in an optimization theory, which you have already learned, somebody might have used about genetic algorithm or Takuchi method or some sort of particle swarm optimization or some sort of any optimization constraint or unconstrained optimization. What is happening is there will be some objective function, there will be two constraints, correct? So you'll be having an objective function which will be given as a learning problem. And for that particular objective function, you'll be having two constraints. Based upon that constraint, a minimization or a maximization problem will be there. You'll be taking the first order differential, second order differential, and finding out some solution based upon that. Okay. Suppose if you have multiple constraints, you will be doing multiple numbers. So some Lagrangian parameters coming into picture where you are using the different types of Lagrangian multipliers, lambda is designated as lambda or any other constant, where you are finding out the different types of Lagrangian multipliers for the different constraints and you finding the solution to the problem. Same way, you have something called as the prediction model f of f1, f12, f13, etc. fn is equal to pn. So it is basically the function that has each components. That is, you can see this f1. So this mathematics I've reduced to a very simple two equation. There are many things which is, so this vector itself can be divided into many components. There is something called as each component of this vector has got the different properties of that. So everything I'm just eliminating, we are designating F11. So F11 itself is a very big matrix. Okay. So F12 itself is a very big matrix. So we can see that F11, F12, etc. F1n is equal to Pi. So that means a function, a prediction model of a function which is having all these fingerprints accumulated or concatenated is equal to Pi. Pi is nothing but the concatenated value of all these properties. So this is very important. So this concatenation of this feature vector, okay, it is in the form of a row or a column vector. It's in the form of a row vector. So all these attributes, each will be a form of a matrix. So it will be having a large dimension matrix which is inside accumulated in this. So this will be a function which is being fed into a machine learning model, like random forest or XGBoost or something like that, and they'll be finding out the solution for this. This is the mathematics behind the system of linear algebra and the mathematics for AI. So within 20 minutes, we have completed this. Actually, this is attributed to a one semester course, not even one semester, a number of semester, five semester course for the mathematics. Why? Because they'll be having the different types of application. Okay, we have seen only some matrix modeling or something called as a decomposition. Something called as decomposition is there. Okay, singular value decomposition, you're finding out eigenvalues and eigenvectors, how you are relating the eigenvalues as a U sigma V transpose. Many things are there. Okay, so each matrix can be decomposed into three. That means U sigma V transpose. U correspond to the column vectors of A transpose. So many things are there. So all these I have summarized in this form. This is a nutshell point of view. What is happening as a mathematics of modeling, right? So here we can see about the another aspect of this. There is something called as overfitting, underfitting, and all. So that is related to the machine learning. So people who are there with the computer science background, or related to that will be statistical background, will be understanding what do you mean by overfitting, underfitting. That is important, but when you go deeper into the take the ML model and doing it, then only you will be requiring that. So here, excuse me, here we can see the target property. So different types of target, supervised learning, unsupervised learning, etc. You can see about what is happening. So here, and this is the idea behind this. So polymer property prediction, ML prediction, DFT calculation. So here, I would like to bring only one thing into the picture. So something called as density function theory, right? Density function theory, we are finding out the values, and then we are comparing with the machine learning. What? Density function theory is a simulation where you are finding out based upon the different types of calculations incorporated by the DFT, right? So this is the idea behind that. So here we have, this is also another simulation, absence of simulations. There are different types of simulations are there related to machine learning, and you can compare it. So these are the another aspects of the property prediction which I wanted to convey at this part, right? So here now
Hello,
comes yes,
Neelesh sir. Sir, I
yes,
have one doubt.
yes, yes,
So regarding this property prediction,
yeah,
whether this AI is doing numerical analysis, numerical calculations behind the software, or is there any? Because as of now, I'm using some method called representative volume element analysis (RVE
yes.
method).
RVE method
So
in FEM.
yeah, yeah. So
Yeah,
whether this AI is
no, no.
comparatively efficient than RVE, or is it
Obviously, it is more efficient than RVE. RVE, I'll tell you why and how, right?
okay? Thank you.
RVE basically what you're doing is you're taking one structure. So, for example, one element or one system from the representing the entire system. Am I correct?
Yeah, yeah.
Reduced
Yes.
volume element or reduced element. What do you mean by reduced element? You are taking entire structure, you are reducing,
Mm.
discretizing into simple elements, and you'll be taking one element for representing the entire structure. Okay?
Yes. Yeah.
But in the case of AI, you are not doing any concept of RV. The entire structure. So, for example, you can see in this slide, this is just a representation again. You can see this entire structure, which I have given the molecular structure also is there. That entire structure is being converted into a machine readable form. And each structural points will be there. No? For example, in the final element, you have 1,000 points or 10,000 points. Each point will be taken in a vector form. That is what I have been representing here. You can see this as a feature vector, right? F1, F2, F3, F4, etc. So this F1, F1, 1, F1, 2, this F11 will be a matrix of say more than 1,000 by 1,000 per 1,000. That means each point it is being discretizing into 1,000 plus 1,000. That is based upon the points we can decide. Then it is being done the analysis. So the result accuracy will be much more and more 1,000 times efficient than that of the RV. Is it clear or
Yeah, yeah, clear.
do I
But
want to
what about
explain
the
more?
solving time? Whether we need more processing power, or is
Obviously,
it
the processing time will be more, but you can use the server GPUs directly. As I told in the Google Collab, we will be getting a GPU server
okay?
connected directly with the Google so that at least within 1 or 2 days, based upon your problem definition, you can solve the things. But apart from that, the I server. So that means the computational efficiency should be obviously more than that of your RBE or IFM. FEM require only 4
Okay.
GB RAM or 6 GB. I'm not saying that you cannot do with this. But the basic machine learning can be done with this. But if you're going for deep learning, if you're having the more number of data set equivalent, so to be obviously taking the server will be required.
Okay. Thank you, sir.
Yeah. Any other clarifications, please? Others, I want you to interact and only. Otherwise, I'll just move on like this. Others, yesterday I had some more interactions. Today I couldn't get anyone. I don't know how many of them simply logged in and gone, but at least very few, one or two, some interactions can be done. Keep it. Okay, fine. We can continue. So here we can see about the different types of fingerprints and related to this. Now I'm just focusing on our general atomic configuration. So body-centered cubic structure, base-centered cubic structure, simple cubic structure. What do you mean by the cubic structure? Crystal representations of atoms and molecules in a different materials, right? You have a closely packed structure. You have a body-centered packed structure. So different types of atomic configurations are there. Atomic configurations will be there. Fingerprinting will be there. Okay, fingerprinting is because this atomic configuration, as I told, we are directly converting that into fingerprints, and each fingerprint is being taken in a bar chart. This is very, very important. Each fingerprints are being taken, extracted in the form of a vector, and we represent the color of the bar chart, right? So this is what happening, the mathematics behind the fingerprinting of atomic configuration of the crystal structure. Now, the same thing, the data generation, you have the data generation, reference atomic configuration images, fingerprinting, again, based upon this. And again, you have the force field. Okay? Here you are using the machine learning, okay, GPR or neural networks or whatever it is. Then again, interatomic potential, we have comparing that. So based upon the different types of materials, this graph will be variable. Amorphous will be different from the crystalline. Diamond is the hardest material, which will be different from the softest material, polymorphism, or different types of beta silicon structure and vanadium structure, or some other different types of low density polymorphism or liquid crystal, semi hexagonal structures. All these are different configurations. So this is the one of the articles which I wanted to share with you. So paper gives the basic concept of AI as a review level. Okay, this I have written in 2024. I think I will share it, right? So another aspect of structure property relations of polymers, which I wanted to explain during this talk, is like we have. Screen is visible now, Manoj?
Yes, it is visible.
Okay, structure properties and relations of the polymer. So basically, the polymers are organic compound made up of hydrocarbons. Okay? So basically, there are two types of structural configuration: crystalline and amorphous. Crystalline is closely packed structure. Amorphous means widely packed structures, or disabled structures, or disoriented structures. So this is basically on amorphous structure. This is basically a crystalline structure. This is the very fundamental aspect of a polymer. Any polymer science person should be knowing this, or chemistry people should be aware much more deeper into it. But I just, since it is my area, I just wanted to give us an introduction slide. So here we can see about the different polyethylene which we use in normal plastic bag. Bag we have P, CH2, CH2. CH compounds are basically the aromatic, I mean, aliphatic, carbon, hydrogen, hydrocarbon compound is directly connected to that. So this the one which is having the dark gray one, or the bigger one, is basically the carbon, and the other smaller one. So you can see the orientation of this. One will be in the rotation or the angular variation of these bonds. Okay, so this governs the chemical structure of the polymer. Right? So as I told, the carbon tetrafluoroethylene, we have CF bonds. CF bonds have highly thermal stability, so that is being used for the our household applications like Teflon coating for this thing. What you can say, Teflon this thing, utensils. Here you can see the PVC, which is for pipes, right? Because Cl bond is there, since it is the electronegatividity of the chlorine and the carbon is there. So the electronegatividity differences of the CCl bond will be there. So it will be beneficial for corrosion resistant application. So that will be used for the PVC pipes. So here where the different types of polymers are there: polyvinyl chloride, polyethylene, polypropylene, polystyrene. Or styrene is basically having the aromatic ring. Polymethyl methacrylate, polyphenol, formaldehyde. All these things are different corresponding. The PET is another polyester, basically used for the biomaterial application. That is for the packaging applications. Okay, nylon 6 is yet another polymer having the nylon 6,6 compound, which is having the very thermal resistance and applications. So wide polymers are available. Different types of manufacturing process are available. Different types of processing are available. Based upon the temperature, there are three classifications of the polymer: thermosets, elastomers, thermoplastics. Right? Thermoplastics, thermosets, basically thermosets are crossed into polyethylene, where you can find the for the dielectric tables where you can find out where you can see that cross-linked material cannot be, for the dielectric cables, electrical cables, where cross-linked polyethylene is XLPE otherwise. Okay, so same way there are different types of thermosets. Rubber, okay, rubber is an elastomer, whereas we can see the different types of elastomer like chloroprene rubber, natural rubber, silicon rubber. Okay, then rubber, which is used for the different natural rubber, latex rubber. All these things are there because all these are the basic of polymers, which we can see the different classifications of polymers, different entities of polymers, different properties, structure, property, relations, process. Structure, property, relation, processing are the four domains in the polymer science. Those who are yet to do a research or yet to do for a PhD or yet to enroll for a PhD, those who want to do a PhD in a different, in a niche area, you can always select polymer science and nanocomposites, or otherwise known as polymer nanocomposites, where you can infuse. It's not because I have done this, as we have done in 10 years back. Now the advancement in such a way that polymer nanocomposite informatics, where you can infuse AI model to property prediction for the manufacturer. So there will be a blend of experiment will be there, computation modeling will be there, HCM will be there, AI will be there, machine learning will be there. So these four clubbed together, if you can do a PhD on that, that will be very good. I'm just deviating from that for 5 minutes. It should be a motivation for those who are there intact also. So those who are interested to do that, you can always contact. There are wide number of opportunities available. Okay, there are a wide number of characterizations available. Apart from the characterizations, we have something called as the this thing, SEM morphology characterizations will be there. FTR spectroscopic characterizations are there. For understanding the chemical bonds, the different types of spectroscopic analysis are there. Okay, different types of magnetic NMR resonance spectroscopies are there. So various number of spectroscopic characterizations are available, which will be facilitated to substantiate and corroborate your results, mechanical results, tensile results, thermal results, dielectric properties, or any XYZ property evaluation you are doing. You can corroborate that with the characterization. This is the advantage of the polymer research, polymer science and nanocomposite research area, right? So here, now we come into the something. So till this slide, directly I have talked about the introduction of the polymers, different types of manufacturing. Of course, I'll just touch what are the different types of manufacturing that, I mean, processing of the polymer is very important. You have something called as a tool extruder, where you can high performance composites, high performance polymers can be extruded. Extruding methods are there, injection moldings are there, okay, compression moldings are there, where you apply high temperature, high pressure, and all these things, and you'll be getting a material. Okay, in case of this thing, elastomers, you'll be using an internal mixer, you'll be using a compression molding, and you'll be finding the molded material as your elastomer rubber composite, right? Same way for you have something called as a reduced tape mechanism. Even for the nano material, carbon-based nano material, the manufacturing is different. Okay, nano fillers are there, different types of nano fillers are there, nano components. So this is a wide area where I'm just opening up this all these topics to you, because your MXCs are there, different types of nano fillers are there, organic and inorganic, organo modified nano fillers are there for your when infusing or when reinforcing with the basic polymer, you'll be getting a different polymer composite, and we can go for a research entity for that, right? Now we see about the piece smiles, okay, otherwise known as polymer smiles. So generally, we have seen only the smiles, which in the last two sessions as well as in the yesterday's session. Now, an extended form of slides which capture the repeated moves, complex constitutively, stereochemical interactions, details in the polymers, which is used for the piece smiles. Piece smiles also available in the R kit. Okay, RT kit pip install piece smiles can be done. Inside the RT kit also piece smiles is available. Basically, the graph-based or grammar-based methodologies transform or integrate polymer structures in machine-readable piece smiles strings for the reliable analysis. So basically, machine-readable piece smiles basically it converts the machine-readable piece smiles, the structure of the polymer, the repeating structure, the complex connectivity, complex structure of the polymers into a machine-readable form. That is the task of what piece smiles does, right? So recent advantage, you can just go through this. This slide also I'll share with you. So you can just see, the difference between the piece smiles and this. So you can see the one which is having the star. So AI take this into action. That means it takes this as a fingerprint. Okay. CC basically will be one of the repeating units, say a monomer, that is being converted in the form of the fingerprint, right? So same way you are getting the different number of n number of CCO is one of the monomer. So like that, n number of monomers will be there to form the polyethylene oxide, say for example. Here it is polyethylene. So this is one of the fingerprint which is being generated by the piece. So many things are learned. Even a PhD can be produced using piece wise itself. The different types of molecular representations. Say for example, 1,000 polymers you take. Different types of piece mounts are there. What is the comparison of piece mounts with other representation? Like that, many number of attributes are available for at the background of piece mounts. Mhm. So basically, here we can see the polymer fingerprints, as I told. So there are different types of fingerprints available, right? So here you can use for this numerical representations like design task, ML based synthesis, PL smiles, moderate, modern fingerprints, Morgan fingerprints, RDK fingerprints, etc. And here we have three links. Okay, three links are available, which I will be posting now. And this will be one of the hands-on sessions which we can do now. So using this GitHub link itself, we can find out the uh, you can find out the different examples, okay, standalone examples of this uh, using PSmile. Okay, so I'm just posting it here. Our next hands-on can be started now. So using this, just open this GitHub link. You can see the code directly available that you can copy paste in your this thing, Google Colab, and then you can run this. So here you can see the different types of. So I'm just posting this. You can open your Colab file itself, and you can do this. Okay. I'll just give you some 10 to 15 minutes. You can start, just explore. Okay. I'm not saying that you have to be thorough with today itself. It's like an interaction talk. So you can just open the link. You can just open your collab file. You can just see to it what is there. You'll be confused at the beginning, no problem. You will get accustomed over the course of time. So you can do that. Okay. So I'll just give you some 10 minutes time, then we can start with the next session of testing and analysis of polymers. So I don't know how far you utilized. Please utilize, because the entire structure which I have designed for this FDP for 2 days is basically one semester course for MTech level or even PhD level course, which we are providing in our university here. So it is not like simple examples and doing it. Simple examples are just the base foundation level. If we cross the base only, we can do that. So people who are there intact online, you can see through this GitHub links and research files, and you can see many tutorials. You can work on this piece minds, right? So I'll give you some 10 to 15 minutes time. Please interact. I want you all to get engaged with at least for 1 hour time. Just open up, you can see what is it, just copy paste and run it. Obviously, some syntax error or something will become, you have to solve that. Or if not, we'll be getting directly the result. So that bugging and debugging, okay, we are learning encoding and decoding are same way, bugging and debugging. We are finding out the errors, solving the errors, then it will be more easy, and that is the best way to learn the coding.
Neelesh sir, these three different links are different databases, right?
These three different links are different database. It's not connected to one. The first one
Yeah,
is different, second one is third one is
the GitHub one is installed in Collab right now.
okay. Remaining one you have to open it and you can copy paste. You have to install the piece files.
Okay.
Piece files has to be installed. From RDKit you can directly click install piece files.
Okay. While running the GitHub Smiles, it is saying cannot run the username GitHub, something like.
Okay. Have you installed the Peace Miles? Pip install Peace Miles in your Google Colab?
Yeah, I clicked on the install button, and I got a file to copy.
No, no, no.
Oh,
No. I'm asking in your GitHub Drive, no? GitHub notebook. You are using GitHub, right? In that
yeah, yeah.
notebook which you are using, there you have to install Pip install Peace Miles. Just try that once.
Okay,
You can just
okay,
search in that, getting the code for installing the Peace Miles.
okay,
The Peace Miles has to be installed in your Collab notebook. Then only this will be working.
okay.
Others, what are you doing? Anyone, please respond. Any any doubts or anything? Please post in the chat box. Okay, I think we can continue. Any clarifications, please post in the chat box. Then we can start with the next session, that is analysis and analytical and testing of polymers, where we can see the different types of testing. So basically, testing, as we have seen, the mechanical testing we know, stress strain characteristics we know, thermal testing we know. Same way, there's something called as fatigue, okay, cyclic loading, or we have fracture toughness. So different types of mechanical testing we have seen in the mechanical and civil engineering labs. So that can be directly associated with the polymer test. But the more important the polymer testing is basically the non-destructive testing, NDT, right? Non-destructive testing is without destructing the sample itself, we can find out what is happening inside the structure of it. So basically, that will be helpful for so-called this autonomous or automobile or health constructions or packaging materials, as somebody were telling about the biopackaging material, cosmetic applications or healthcare materials, biomedical applications. So for all the biomaterials or biopolymers or biocomposites, something called as 3D printing comes into picture. So 3D printing means we are printing out the different types of structural configuration based upon the requirement of the customer. Then they'll be using the highly rigorous testing for their property, like accelerating temperature conditions, accelerating pressure conditions. So, for example, for the space applications in ISRO or for the radiation resistance applications in DRDO. So, what they do, no, they'll put this polymers in an accelerated radiation dosage chamber where they'll be finding out particularly how much time will be there, how much temperature conditions will be there, how much radiation conditions will be there. Everything will be put in one chamber where it is being given an accelerated dosage of say for 10 years. So how much the polymer can withstand for 10 years or say 20 years? That will be your idea behind the polymer testing. So basically, this is the idea behind the polymer testing. So gathering information separately. So I'll be sharing this slide so that if you have it, suppose you can point to this. Just reading and wasting your time, so you can just see to for that introduction. Now, the comes into the main important factors, one of the most important factors, apart from molecular presentation, is composition-based feature vector. So basically, the composition-based feature vector is basically this is a composition of feature A3, A2, or G2, A3, C2. So all these are converted to numerical vector having the properties like atomic weight, atomic number, electronegativity, melting point, radius, or something like that. Apart from this, there are many molecular properties, like some molecular number, say something like that. Your atomic number, molecular number, or say molecular weight density. So something called as all these are kind of the attributes which is being designated in the form of the numerical vector, right? So this is the pinch of CBFE import pandas. So here in front of article, you'll be using pandas in the library, and CBFE.cbfe composition import generate features means you'll be finding out how these features can be generated from the pandas library, correct? So here this is the generate features, and MapPy is another property database where you can find out the property of the entire compositions, okay, different types of compositions from the elemental database, right? So this is the idea behind this, and you can see that code is also given. You can have the you know practice session based upon this code. And here you can find out the values of the CBFE directly corresponding to this. And here you can see this is all the worked out examples which you are doing it and which you are doing. So CBFE is also another area where you can focus on, which is based upon all the particularly for each benzene, acetic acid, styrene, acetone, ethanol. All these are the different types of polymers in one state, and you have some target variables for this is actually a binary vector where you either 1 or 0, 1 or 0. Like if you take 11100, you will take extracting three features from this. So it will be taking extracting the features from MapPy. MapPy is basically a benchmarking data repository where you can extract the features, right? So same way as another example for that. So this is actually the workout example for all this. For just I'm not moving away directly, skipping the slides. I don't know how many of them are there. So you can start doing this as a using your collab itself. You can do it or using your Python library where you can install your pandas and articles. This is the end of this molecular representations and mathematics for a year, right? So I think you can start doing this because this is the practical session where you can do this. So I'll be sharing the PPT with you. So I'll be sharing the PPT with you. You can Well, I'm just sharing some PPTs. They can start working on
Yeah.
this, right?
Yeah, sure, sir.
Yeah.
So,
So with this our this thing over, so they can this the last slide which I have taken. No, I think yesterday I
yeah.
shared with molecular representation. Today I'm sharing these one, two slides with you. So these two they can do enough and more for the session as a beginner level, right? Then if they
Okay.
are, if anybody is interested, so I'm just opening for the thing and closing the session. Anybody is interested to collaborate or anybody is interested to work more deeply into it, especially in the polymer science, chemistry, biology, or any diverse background, analytical background also, dielectric properties we are doing, dielectric materials we are doing, material science, those who are interested, those who want to get in touch with the knowledge or research idea. So either as Amarnath was saying yesterday, either you can perish or you can flourish or they say which one basically you have to flourish. So you have to, if you want to flourish, you can directly associate with
So,
AI technique. Yes, please.
so also, I think if anybody wants to connect with you, you can share your email ID
Yeah,
here.
yeah, best.
Yeah.
Email ID is there, mobile number is there, everything I'm sharing, right?
Okay. I have posted it in the group.
Okay.
If they have
Okay.
any doubt, I think they will contact you.
Yeah. Let them contact.
Yeah.
These are the two email IDs. Anytime they can contact. I
Sure,
think I
sir.
have only one request. So they're online. Please don't leave this as of now and go on. Please take it as a very good opportunity. It will be beneficial for you in some way or other. Okay. So here we have 8 programs: AI in data science, in that AI in medical engineering is there, AI in quantum technologies is there, AI in autonomous agents and robotic system is there, AI in cyber physical system is there, computer science with AI is totally 8 batches of around each batch will be having 60 to 65, 70 students. So around 500 students are there each first year, second year, third year, and final year, right? So this is the idea behind the advancement of AI. So people humbly request those who are not having an exposure, don't worry. This is the time. You have your ChatGPT or Gemini or anything is there at your fingertips. You can get any error solved. So people here, even the dean is being suggested to solve the errors by using the GPT sources, right? So earlier days, people used to go to Google, people used to get the commands and they have to learn the coding. Now, coding is there in your fingertips. Only thing is that how to track and how to, develop it, right? So that you can focus on. So this will be a primary starting point. I'm just sharing very few materials which I am having out of this week. If you want, n number of materials are available, but you have to take interest. Simply giving the materials won't be helpful anyway. So you can have the starting point, then we can have a brainstorming session. Whatever collaborations or whatever things, whatever I can do, it will be helpful for you. I'll be doing it as a right. So with this, I'm ending this session. So anybody who want to interact now, you can open your mic and say anyone. Anyone? Manoj, available or I have sent you, no? One of you got it, right? You can post in the group.
Yeah. I have shared the PPT in the WhatsApp group.
Nothing else, Sumrat. I'm just leaving the session. I think nobody is having anything to say or
Yeah.
anything. Yeah.
Sure, sir. Thank you.
Okay. Thank you.
In case they have any doubt, they have your email ID. They will
Email ID is
contact. They
there.
can contact
Yeah,
you.
contact number
Yeah.
you can give. Anything you can
Yeah.
give, no problem at all. Anytime they can
Sure.
contact. Yeah.
Sure, sir.
Thank you.
Thank you. So I'll share the Google feedback form right now in the WhatsApp group also. Please give a feedback. Thank you.